Welcome back. This is part 4 of a universal modeling framework for sequential decision problems, bridging machine learning and stochastic optimization. In part 4, I'm going to start off by talking about how to optimize a parameterized linear program. So let's take this energy problem where I can pull energy from a wind farm with highly stochastic supplies, or pull it from a grid, infinite supply, but wildly varying prices. I need to meet a fairly predictable load, that's the demand, and I have a large battery to handle variations and fluctuations. Now, one of the challenges with wind is that it's very hard to forecast. This is real data taken from PGM interconnections. It's over a 24-hour period. The black line is the actual energy from the wind farm over the 24 hours. And then there's a series of forecasts. This is the first forecast starting at midnight, and then it's updated hourly. You can see that these forecasts change quite a bit. So wind further than 4 or 5 hours out is very hard to predict. Now, what I'm going to do, I struggled with this for several years, trying, by the way, to use different forms of approximate dynamic programming. I finally gave up and did an old-fashioned deterministic look ahead. This is a linear program where I'm looking out 24 hours into the future on a rolling basis, and there's our wind forecast. So that little FE will come to this linear program as a number, acting like it's a rock-solid number, when in fact we know that, say, the forecast for 2 p.m. when it's midnight is going to change quite a bit as we get closer and closer to 2 p.m. Now, there's different ways to handle this. What I did was to say, well, I don't know. Gee, if that number is pretty soft, maybe I'll just put a factor, a coefficient in front of it, and maybe see if we can discount it. Now, the way to think of this parameterization is just as if you were a machine learner. Now, let's say I've got a machine learning problem. I'm trying to predict demand as a function of price, and I have an idea that the higher the price, the lower the demand, but I don't know much more than that. You know, one crack would be to say, hey, just do a line, downward sloping, and maybe that captures the fact that increased price reduces demand, but I might not be comfortable with a linear relationship, maybe an S-curve that I get with a logistic function. So choosing between those two functions is there's a certain amount of intuition and judgment having to be used, and then we come in with algorithms to find the best fit. So what we're going to do is, let's say I'm given what these parameters theta are. Now I'm back to having a simple deterministic linear program. It's very fast to solve. By the way, it's just like Google Maps. And at each hour, or you could even do this every 5 minutes quite easily, I look forward, optimize, figure out what to do, roll forward, update the forecast, update anything else, solve the linear program, and I keep rolling forward. In the field, this is very easy to implement. So what we're doing is we have a policy that is a deterministic linear program. The objective function is how well the policy does over time. By the way, simulating these policies can be quite noisy. Now, the stochastic optimization problem, I want to come up with the best parameterization. So F there would be my choice to put theta in front of the forecast. But you could put thetas. I can make it multiplicative. I could make it additive. I could insert thetas in other places within the linear program. This is intuition. This is what a human has to do. But then once we've picked the parameterization, I still have to tune it. I have to do the same function fitting that you do in machine learning. Now, for this work, which was done by Said Ghadimi, who was postdoc at the time, he used Jim Spall's SPSA algorithm. There's other algorithmic strategies you could use, but we found this very effective. Now, here what I'm showing is the progression of the results for different parameter choices called a mini batch. Now, the mini batch, because these simulations were very noisy, we would run them multiple times and then take an average. So that yellow line, that dot, is where at each point where I run the simulation over all 24 hours, add it up. Remember, each one of these linear programs is being solved to optimality, of course. Now, as we adjust the thetas, the results in a noisy way generally improve as the algorithm progresses. But I will emphasize that each one of those yellow dots, I have solved that look-ahead model optimally each of 24 times and added up the performance we get from the solutions that are implemented. Now, we started off with a test that says, what if our forecasts are perfect? And we would expect that the theta should equal 1, and they do. The optimal thetas. Now, each of the thetas, we have a theta for 1 hour out, 2 hours out, 3 hours out, all the way up to 24 hours out. So with perfect forecast, the optimal thetas are all equal to 1. But when we go to the imperfect forecast, we get something that's much different. This blue line is for the 1 hour out. We get an optimal theta somewhere around 0.7. Then there's a cluster for 2, 3, and 4, and 5 hours out. Here, where it looks like the algorithm prefers a much smaller value of theta. 6 hours out down here, looks like theta equal to 1 really is the best performer. Now, obviously, we could do different parameterizations. This is a great area of research for somebody who wants to get into it. But for the most part, choosing the parameterization just as it is in machine learning is a bit of an art form. Now, we did a number of different runs. This is what we get when we fix theta equal to 1. And then we optimize theta. We get about a 30% improvement. Now, tuning the thetas is not easy. Parameter search, these are very noisy simulations. This remains a challenging algorithmic exercise, but that's in the lab. Once you've optimized the theta, you go to the field, and the model is just as easy to solve as any deterministic solution. Okay, now I'm going to talk about choosing policies. So we took this basic energy problem, and a different postdoc, Stefan Meisel, who's now at University of Twente in the Netherlands, created 5 different variations of this. And we played around with whether the forecasts were highly accurate or not, and how noisy the prices were, and that sort of thing. We created 5 different policies, one from each of the 4 classes, and then a 5th one that was a hybrid. The hybrid is the one that I just showed you. It's a look ahead. It's a DLA that plans into the future, but parameterized so that I can tune it. Notice that we made each one of these 5 policies work best on one of the problems. So we don't have a magic wand here, at least for this application. You have to be able to choose among those. Now, there will be other problems where, for example, routing my way home, I'm going to use Google Maps. That's a DLA. I don't think of any other way of finding a path home, even in a dynamically changing graph, other than with some form of a look ahead. Now, let's get back to our bridging between machine learning and sequential decisions. Now, when you're if you limit yourself to policy function approximations, PFAs, the different functions F can be any function that you might use for machine learning. So if you have strong skills in machine learning, the only difference between doing vanilla machine learning and sequential decision problems is machine learning, you need the big data set. You don't need an actual model of the problem, but for sequential decisions, you do need a model of the problem. You need an objective function, and you need the physics. Now, we still have 3 more classes of policies, each of which is its own optimization problem, possibly, usually with tunable parameters. Now, let's take a look at what the academic community does. We've got these 15 different fields. It turns out 10 of these either work exclusively with Bellman's equation, or they use Bellman's equation along with some 1 or 2 other methods. Now, when they don't do Bellman's equation, they're all doing look-aheads, especially stochastic look-aheads. So methods based on Bellman's equation or stochastic look-aheads absolutely dominate the academic literature. Now, I've taken our 4 classes of policies. The 4th class I'm going to divide into 2 categories, deterministic look-ahead and stochastic look-ahead. Then I'm going to divide the stochastic look-ahead between problems where the action is a discrete action, red, blue, green type of thing, or whether the decision is a full-blown vector. So now I have 6 types of policies, and we can ask the question, which are the most useful? Based on my experience, decades of working on a wide range of problems, category 1 is the category that is absolutely by far the most widely used, and this consists of the PFAs, which are rules or analytical functions, CFAs, which are parameterized deterministic optimization that doesn't look into the future, or deterministic DLAs, which do plan into the future. Absolutely, category 1 is going to cover, 97% of all decisions. This is something that everybody needs to learn. I claim every human already knows to use these and adapt them to the right situation. Now, category 2 is still useful, decision trees. Decision trees are when we have that look ahead, but we have to deal with uncertainties. These problems absolutely arise, and work with decision trees is well known, certainly in business schools. I would even argue that somebody untrained can still handle limited uncertainty in a look ahead policy. So category 3, I've got this all in its own category, are the policies based on Bellman's equation. I've got a 600-page book. I spent 15 years of my life working on how to compute and approximate Bellman's equation. My conclusion is it's a very powerful strategy for a very small number of specialized problems, much smaller than the number of problems that you actually see in the literature, and I know this from personal experience. So all by itself, category 4, absolutely in my opinion, the least useful is something known as two-stage stochastic programming, originally introduced by Bellman. There's a community that likes this. So far, I mainly see journal articles about it. It's very hard to find people admitting to real-world applications. Now, I sort of feel so strongly about the difficulties of using Bellman. I put together a series of LinkedIn posts that you can access, tinyurl.com/why Bellman does not work. And I sort of make the arguments of, okay, this looks good on paper, but it's awfully hard. Now, this is the approach. Originally, reinforcement learning was entirely focused on approximating Bellman's equation. And most people, when they say they're using reinforcement learning, are talking about Bellman's approximation. But if you go from the first edition of Sutton and Bartow's well-known classic on reinforcement learning, which only looks at approximating Bellman's equation, to their second edition. In their second edition, you can find examples from all 4 classes of policies. Now, why would they have those other classes of policies? Well, it's because approximating Bellman's equation is hard. And while we may be able to get it working in an academic paper, in a journal publication, as a general tool, it's just typically not going to be the tool that you end up using. Now, let's go ahead and now compare machine learning to using parameterized policies. Now, with machine learning, I have to search over functions like my linear function or maybe my logistic regression, and then whichever function I choose, I have to do parameter tuning using a training data set. If I limit myself to the parameterized policies, the category 1, PFAs, CFAs, and deterministic DLAs, I can parameterize all of them, usually do, and I have that parameterization. Now, when you look at machine learning and stochastic optimization with parameterized policies, it starts to look much more similar. Now, this is a very different way of thinking about optimizing in the presence of uncertainty. I think it's much more powerful and a lot more practical. So now I'm going to come back to my slide with Danzig and Richard Bellman that I introduced in the very beginning in part 1 of this talk. My conclusion is that linear programming is a very useful modeling strategy, but in the broad array of decision problems, it's only good for the most complex decision problems. And by the way, and most of these are sequential. You don't just solve them once. Whereas sequential decision problems are virtually universal, something that we all encounter every day, but we almost never use Bellman's equation. Okay, it's limited to a small number of applications. So this is a fundamentally different way of thinking about optimization. Most optimization problems are sequential. Most of them use simple decisions. The hard part is dealing with them over time, but we're not going to use Bellman's. So I think it is time for us to change how we approach optimization. I've put together a very short book for instructors mainly. I wrote it with the idea of changing how an introduction to usually linear programming is taught either at the undergraduate level or master's level. So I've broken it into 11 topics. The first topic is machine learning, where we have to pick the parameters for a problem, and it introduces the idea of parameter tuning. I do both linear and nonlinear regression. Now I use that as the foundation for topics 2 through 6, which are all sequential decision problems and simple decisions. Okay, not the big vectored value stuff. Now, starting at topic 7, this is when I first introduced linear programming. I use a network model so you don't have to do some toy two-dimensional problem to understand it. Now, I do linear, integer, and nonlinear programming, and I do each of them two ways, static and then sequential. So sequential linear programming, I think, needs to be taught, but not with Bellman's equation. Thank you very much. This is the end of part 4, and look forward to seeing you in part 5.